think you could help us with any of these things, send us an email at contact@tokyorobotics.org. Raise your hand if you're working on robots.
Oh, a lot of roboticists. Okay.
Oh, that's a lot of people. A lot more than I expected. All right, so this should be exciting. Today's event is about Copper, which is the OS for physical AI. Our speaker is going to be Guillaume, who's founder of Copper Robotics. Guillaume and I met at Rust Asia in Hong Kong last year. Had great conversations about robots, Rust, frameworks like ROS, C++. So I'm very excited to hear his talk. And with that, I'm just going to hand it over to Guillaume to tell us about robots, Rust, and AI. Thank you.
Hi, everyone. Thank you. So I'm Guillaume, the founder of Copper Robotics, a company I started like 2 years and some change ago. If you want to connect with me, I have here my LinkedIn account, or you can do that a little bit later. A little bit of my background, I've been mostly like in self-driving space with Argo AI and Motional as an executive, but I've always been like very technical. And often I say like Copper is basically my fourth try. Like I made like or try to either make or fix like kind of like what was Copper at those companies, and finally I say okay, I need something for everyone. So that's how I started Copper. Usually, so that's funny, right? Like because we have a kind of a mixed audience today. But usually what I do is I present Rust for roboticists. Like Copper is kind of part of like that larger community called like Rust for Robotics, because roboticists are very conservative, right? Like they don't like to change. They don't like to change their tooling and so on. Like if something works, don't fix it. And so we organized the like the workshop at ICRA last year. That's a IEEE like a huge conference for robotics for people who don't know. And this year we have been selected for IROS, which is a little bit like another like a more like kind of like researchy, more researchy type of conference. So yeah, it's going. So that starts to be known that like yeah, actually Rust is working pretty well for robotics. But for you guys, you're part of the Rust community, so it's more like robotics for Rust than the opposite. And so sorry for the I don't know. I saw like a third of the people that are already roboticists. I'll say stuff that you probably super obvious for you, but like for people that never touch hardware or robots might be actually kind of new. So I'd like to start with like a little demo, if it works. Like please pray with me, the gods of the demo. I don't know how to do this. Like I never made that successful. And for people who know Rust, that's just a cargo run. It's starting like a simulator, if it works. Yeah, it does. Okay. So to demo Copper, I usually use the simplest robot I can find. And that's basically like in that virtual world, right? Like a rod that is actually self-balancing. If I touch it, like if I push it, like if I were to push that in the real world, I have that for real in my office. It self basically actuate the bottom, so to be sure that the thing is actually well balanced. If you push it, of course, like a little bit too, if you wonk it, you see, it can fail and so on. But I can reset it, and you will find back that space. Okay, that's a very simple robot. Like what a robot is basically a machine that observes the world, kind of try to take decisions on that world in real time, and act on it, right? Like so, sensing, algorithms, and actuation. And like when you look at Copper, it presents you like actually the internal state of Copper, and it represents basically from left to right that paradigm. So you have like components, like for example the position of the rod, the position on the rail at the bottom, right? You have like PIDs, which is an algorithm. You know, if you're a roboticist, you of course know what it is, but if you're not, you probably don't. And it merged like those two pieces of information with like kind of a state, and at the end of the run applies a force on the bottom to try to actually balance it, right? So that's usually how you design robots. Of course, today you have a lot of things where this big box in the middle is actually end to end, right? You actually get like an AI model, and you teach it like, oh, you know what? Those are the inputs, and give me the outputs. But that doesn't change the concept. So now you would say, okay, Copper, right? Like we do have already like a huge like a community today, an open source community that is with like a lot of company contributing components and so on, called ROS. It's called the Robot Operating System. It is not an operating system, so we'll go through this. It's basically the same concept of task, right? Like where you have like what you saw with Copper, right? It's mainly in C++. Now you can use Rust, but it's like super wonky. But yeah, historically it has been C++, so usually the native way of talking to Rust is actually C++. A lot of people also use that with Python. And so that's interesting. Their goal was more about flexibility. So you know what, when you are building a robot, that makes sense, right? Like, because you don't know what you're doing. And also a robot is usually co-developed with a lot of things, like you develop the sensor, you develop the calibration for the sensors, the algorithms, and so on and so on at the same time. And you need that flexibility to be able to swap components, like upgrade one, try out something quickly in Python, like pop up like a task and so on, to actually experiment with it. So I understand where they're coming from, right? Like when they at Willow Garage, like the company that started that, and they wanted really something that looks like a microservice. Like literally, they did that during the hype of the microservices, and they wanted to replicate that. The problem of that is that first, a robot is completely, that's why they pick that too, right? It's completely asynchronous, right? You can imagine like your sensors can actually publish data at any rate, at any time, any point. Like like an interrupter could be shorted, whatever. So it's kind of asynchronous. So that kind of makes sense. The thing is like, but also it's non-deterministic. What I say by non-deterministic is like if you take ROS, it has a way to actually record data out of your robot. Cool, you say. Cool, I will make those ROS bags, it's called ROS bags, out of my sensor data, and I want to, record something that the robot is doing, and then try to reproduce that on my machine. That's almost mission impossible with ROS. It's non-deterministic. We'll see a little bit later why it's a problem. And a problem is like, the C++, you can imagine roboticists are not software engineers, right? Like, okay, people can be very passionate with C++. I've known like a lot of people very, very strong in C++. Yeah, you'll be like completely geeking out about like one of those strange like undefined behavior. Robotics have no time for this. He has the hardware, he needs to solder the thing on the motherboard, fix the calibration, and oh crap, my power supply just blew up, right? So not a good language for in my opinion, to put in the hands of somebody that really don't care about like the language they use. The performance is terrible. So the microservice architecture, it makes sense when you think about it because of like the modularity, but it has been invented for throughput. It has been invented for the web. Like, okay, you have 10,000 million people hitting your service at the same time. Yeah, you scale up in bandwidth, not in latency. In robotics, you care about bandwidth, but like the critical thing is latency. You need to be able to react to the world as quickly as possible. In practice, it's just like C++. You have dependency with the system. So we were talking with Matej about like those like you need like either like like containers or something to be able to actually give to your raw system all the local dependencies. All in all, it's very challenging to put in production and like how can you try to safety certify that thing? Is just impossible. So how did we fix this? So we built Copper, -RS for Rust. It's a Rust first SDK and runtime. It's even a little bit more than this. It is like an actual operating system. You can actually deploy that on microcontrollers. And yeah, oops, sorry. So I say like a software engine for robots often, and I'd like to to explain a little bit like where we started from, like which first principle we took, and I basically stole a page from the gaming industry. That's funny because we have a gaming engineer in the room too. Do you know those games? Hey, who wants to be really dated in here, right? Which one is this?
It's Persia.
Oh, nice. This one? Oh, come on, a classic. And this one?
Fortnite, I guess.
Fortnite, yeah. So that's basically like really like 3 big steps we had in that industry. That is really interesting. So, now that I had like several Prince of Persia, do you know how was animated this little character?
Rotoscoping.
Yes, right. So this person with I think his son actually made the.
Maybe his brother
Or a brother or something, right? Like somebody from his family actually got filmed with a rotoscope and they scanned the scan lines for the pixels, and they had like those like great animations back then. It was like, oh my god, so fluid as animation, right? And everything was encoded in assembly end to end, right? So you see, that's basically how robotics started. Like you code everything like from scratch, like bits and bytes. You don't have like a lot of like leeway. Nothing is really reusable. I don't think nobody reused anything from those. But something changed around like that time around Doom, right? Like because suddenly like all those games that were really hand coded one shot, suddenly you had a game engine, and that changed completely the face of the industry. And basically, that is just an evolution of the other one, right? And the big thing for me, right, like about like what you do there compared to what you do there is like you split the problem of like how fast your game will run, how it will run, and from like the assets, from the sounds, from the scripting, and so on. Like you start to split your product and have like a view for like people that are not computer engineers, right? There, nothing was not computer engineered, basically, right? Everything was a computer engineer. Here, now you have like people that just produce music or like sounds or sound effects or 3D modeling or and so on, right? And that's a little bit the vision I have like behind Copper, right? Like you should be able to have something that runs super fast, reliably, that is not just a demo one-shot thing like you see in a lot of like those like robotics like conferences, but something that is actually in your living room, and readily accessible for everyone, because you could have like those people that are coming from like all sorts of like specialties, from controls to AI to I don't know, EE and so on your robot. Oh, we didn't like it. Yeah, so how does it work in ROS? Because there are microservices, you can see those messages that are actually flowing through the system, right? Like kind of like asynchronously and buffering. But in Copper, we don't do that. We make kind of like ahead of time a scheduler, and we execute always the same loop. We don't have any asynchronicity in our system. And if you know how games are made, that looks like a game loop. So imagine Copper basically gets that description you saw before, like with those those modules. Guess what would be the scheduling that would match the best for that kind of graph you gave it, and build like a specialized game loop for your robot. It goes like a bit like more complex than this, because you can parallelize stuff and so on, but that's the concept, like the core concept behind it. So the analogy goes well, right? So conceptual view, you implement like your tasks. That infers like an execution plan, And you can then deploy and test and collect data out of it. And then that's not done yet. We are working on it. But the ultimate goal is basically take that data and basically make something like PGO for people that like compilers, right? Like profile guided optimization, like kind of getting like what happened on your robot in terms of like execution, and try to infer a better execution plan, better scheduling for your robot. So that's the overall plan. We are there. It already works very well. Actually, we have a bunch of like robots already running on that partially implemented Copper, let's say. So core concept is deterministic by design. So it means that you run Copper on your robot, you get the data out of your robot from a run. You strip out all the intermediate data or output from your logs, you replay that log, and you compare the output, and byte by byte is exactly the same. We test that at every single like commit you put in Copper. So that has like a lot of like interesting properties. One is for those developers, right? Like it means that you can build like a CI/CD where you make test cases with like good exit conditions for your logs, and they won't flip-flop because like some threading or some like concurrency would happen like it would with ROS. So you kind of like a solid base for you to know like when you change something in your code base, your robot is actually progressing or not. Sounds stupid for a developer, for a roboticist, that is mind-blowing, right? So it has also another interesting property is it is a pathway towards safety. So let's go into like more robotics and especially autonomy. So when we talk about autonomy, like it's all about robots that would like kind of navigate in like unstructured world. Like you will have like, let's say, for example, a self-driving car or a drone or like any of those like robots like in like, let's say, in a family home or something. You cannot actually foresee exactly every single conditions of what they will see or encounter with those environments. I don't know, like a piano falling from the sky, somebody getting out of a manhole for like a self-driving car and so on, right? So the name of the game there, when you want to kind of like make a safety case for your robot, is to be able to accumulate like all those test cases and say, hey, you know what, like in my operational domain, basically what I expect, where I expect my robot to navigate or operate, I basically it's continuous, and I have enough like samples in my data set. That's why like Waymo did like millions of miles, right? They wanted to cover their operational domain enough to say, hey, now I can say that with those conditions, I can say it's gonna be safe. But wait. Like if your auditor comes in and says, yeah, you tested all that, now prove me that what you actually executed in your test is what is happening on your robot, with ROS, you're dead. That's it. There is no way, you have no link between what you have tested and what is executed on your robot. And that's what we fix with Copper, right? That's why we have a strong path towards safety, and that's what we are working on right now. Actually, we are basically building the documentation for helping those companies to build a safety case on top of Copper. And it's so another thing, like in terms of robots, a robot is a finite quantity, and I think like a lot of people are coming into that discipline, even like a software engineer, saying like, yeah, those are computers, you can, yeah, it's okay, next year there will be like faster RAM and so on. No, right? Like now, like gains are kind of marginal, and the more you add, the more power you use. And let's say humanoid robot, it has a battery, right? Like so, you can't put like a data center in a robot. Usually, you don't want them to communicate to the cloud. So it's a finite thing. So every single cycle, exactly like a game, would count into like having your product that is usable in the real world. That's why we are like, high bandwidth, low latency, and low jitter. We are like 100 times less latent than ROS on the default configuration. And we also focus on like what I was hinting a little bit prior, in terms of like APIs, even if we are with Rust, we massage that so people can really focus on their algorithms. So if you were to talk to you as Rustacean to like a roboticist, I would strongly encourage them to explore, for example, the functional side of Rust. When you look at the functional side, like you do, you know, filter, maps, those kind of things, zip, and so on, it really looks like Python. So show them like a little bit like the example in Python. That's what I do with like Rust for Robotics, showing them a little bit of Python, like functional Python, functional Rust, and you're like, it's basically almost like a keyword translation type of thing. And yeah, it allows there to tune the system as you iterate on it, like with like the metadata we have. Like that's the performance. I don't want to bore you too much. Like also we are logging only linearly on disk. So that's why we have our own file system because we don't need a file system. We just append stuff. So and yeah, out of the box, like Rust 2 use like SQLite, which is absurd, right? Like it means like your robot, when it runs, when it wants to record data, it starts to build an index so you can actually query your data. Why? Why is it the time when you have, I don't know, somebody in front of you that you're, oh yeah, let me insert in that B3 some index somewhere. I don't understand this design. No, you log the data and you'll see that like later, right? You can always index later. That's what we do. We do also support MCAP, which is another format that is kind of like fixing a little bit of what they did like with SQLite. We are still 12 times faster. Like I was saying, so we run everywhere. That's the beauty of Rust. I mean, I've been like blown away by Rust for this, right? Like literally, if you go to the homepage of Copper, you click. I built it for WebAssembly. You can run Copper on a browser. I was like, what? But yeah, all Linux, macOS, Windows, Android, even I didn't even try. I didn't even try. I just compiled it. It worked, right? But we are actually an operating system, right? We have a scheduler, we have a file system, we have like a monitoring system, and so on. So we also run bare metal. We can run like drones, like on STM32s, and you can mix and match, which is super cool also compared to Rust. So basically, maybe you have like a high-level thing that would work with your high-level AI algorithms on Linux, with like, I don't know, an NVIDIA accelerator or whatever accelerator you want. Some part that is working on, like, let's say, control on a low-level MCU. You take those tasks, you recompile that as one process on your machine, and you can replay or replay what those two machines that were completely different, like a bare metal and high level. You can replay that as one on deterministically on your desktop. So again, you say that to a Rust developer, a Rust user, like that's literally impossible. So first, like on the left-hand side, impossible. That's micro Rust. It's completely something else. That's not. It's just like so. Yeah, it's like in the future for them. A little bit like off code. Of course, we are with Rust developers. So how do we build that? We use run, which is like I think Rust object notation, and we have a kind of a syntax that points to types in Rust, and that's how we are modular. You can connect them from one to the other. The little connections are actually defined like this. You have like some configurations, so it's you can actually add like some variations for your configs. You can compose them. You can compose systems. That's how we can have like several ones. You can even like make like a swarm config, like several like drones that are talking to one another. So it's very flexible, and that allows like people to focus on like again, like there will be people that configure robots or like do like calibrations and so on. And there will be people that actually program robots. And that allows a little bit of that differentiation, right? Like so that would be touched by maybe different people than the people actually focusing on algorithms and tasks. And that's how it looks like internally. So one thing I did that is actually helping people implementing tasks that are coming from other languages is that I present already the input and output. So for example, here output already typed with like the correct scope. So you have like a mutable output and a read-only input. And usually it means that when they are building the algorithms, hitting the borrow checker is actually kind of late. It's when they are starting to build really something complex, and if they decompose their robot like pretty well, usually they never have to touch that. So if they are like on top of that, you using functional programming, you usually avoid those kind of things because you are in the pure function type of territory. That speaks well for people that are doing math, and for them Rust is not even the equation. You need to add like some things like, okay, the configuration there, and you need to be able to actually store your own state. So we have a kind of keyframes when you are recording. We can actually completely serialize your entire state of your robot, and that allows us to replay and jump like into like specific things. Like imagine, okay, even if you are deterministic, imagine if you have like 1 hour of like running logs. If you don't have a way to actually jump somewhere and restore a state, it's going to be really hard. So we have that feature there. You can do that either on the robot or actually offline. You can actually not put any keyframes on your robot. I would not completely recommend that because sometimes like, logs get corrupted or power gets cut and so on. But you can still do that or reconstruct those keyframes after the fact just by replaying deterministic your robot at ingest, right? At log ingest. And we are like we do use like the standard Rust compiler. So that's also something that was important. Like Rust is so good to actually with the tooling. I did not want to make like kind of like a meta tooling on top of it and so on. Just the way we have a kind of like a template. So if you want to start quickly, you have like a cargo new, but for Copper. But that's the only thing that is different. Like if you want to build for your robot that is on ARM, it's there. For in terms of like so a question I get like a lot from Robotics is like, yeah, the ecosystem in Rust, how is it for robots? Because like with C++ and Rust I have a lot of things. The interesting thing is like the community is actually growing like very, very fast, and they are producing like they are coming from like me a little bit. Like this is not their first time. Like see Cornia, they actually had their C++ like computer vision library. They say, okay, I will rewrite that in Rust, but not like just port it in Rust. It's going to be okay if I have the opportunity to rethink about what I'm doing, and they did that from scratch. And a lot of those, like Xeno is like a kind of a middleware, X2, Rerun and Foxglove are more in the visualization. Fire and Algebra are more like on the algebraic things. You need that a lot in robotics. And all of them are absolutely amazing. Like interesting, it's not because it's Rust, it's because like those guys just stop the clock and actually rewrote like their V2 of what they dreamt of when they started a long time ago. And Copper is one of them, right? Like so you can find us on GitHub, please. If you like it, add the star. It's always appreciated on the GitHub repo. And we have a little bit of swag, but I'm running out like of it. Like it has been, I've got ready, so I have a little bit of that. So I think it's time for questions.
We have a long-standing tradition, Tokyo Rust, to ask the speakers some personal questions about their background. So I'm going to do that. Are you prepared?
It's going to get personal.
Very, very personal. Thank you for the great talk, by the way. I really like the analogy that it's like a game engine. I actually got into computing because of games, so I really like that.
What was your first computer? I preempt the personal questions. Yeah.
Good question. I'll go with it. My first computer was a IBM PC 286.
Oh, nice. CGA or EGA?
I think it was VGA, actually.
Already on 286?
Yeah.
Oh, nice. Oh, okay.
I'm that young. You know.
Oh, wow.
And another main thing was that it was not powerful enough to run any of the interesting games, so I got into programming. Yeah. Anyway, so it's my turn now. What programming language did you use, or programming languages did you use before learning Rust?
Yeah, so I have 10 years of Java, but you won't find that in my resume. I'll try to erase that from my memory. Also like a decade of like C++ also, like in self-driving and so on, they were not using Rust at all. They were using C++. And as much in Python actually. I still use Python. Like it has its place, like especially with AI and scripting stuff left and right. But like that's a little bit my language journey, let's say.
All right, so Java, C++, and Python. So that covers a lot of ground in terms of language features. So what did you find difficult to learn when you were learning Rust?
So what surprised me is how easy a lot of things are in Rust actually. Like setting it up, like running things and so on. Like the error messages. Like even if you struggle a little bit with Rust, like the error messages are so good that you can learn from the compiler, which is like amazing when you think about it. But still, like anybody else, like the borrow checker is probably the one that I took a while to get ready. But I strongly believe that it makes you like a better programmer. Like I've seen a lot of people learning Rust, like getting beat by the borrow checker and suddenly changing their like me, right? Like taking a few months to actually learn the patterns about how you should structure your code in a safe way. And they do reapply that in other languages in C or C++. So definitely the broad checker. But overall, like that's honestly one of the easiest language. I except for this that I now learn. I was like productive like with .clones everywhere maybe, but I was productive pretty quickly.
What advice do you have for somebody who's just starting out that can make their life easy learning Rust?
So for the roboticist, I mentioned that like mimic Python in the functional side of things. For like general programming, I think do feel free to actually do several versions of your program. You won't get it like right away. Don't get frustrated. Don't get like me trying to make it perfect at the beginning and trying to fight the broad checker. Just clone your thing, make it slow, understand where it is not good enough. Try to refactor it like bit by bit. And now with LLM, you do have a way to actually, LLMs are actually good to go around the borrow checker, so you can actually, they can help you actually understand what's going on. And that's a little bit scary because like some people might never actually go into it and just let the LLMs fix their thing. But still, I think that's really important for people to understand that deeply.
When we chatted previously, you mentioned that you feel like it made you a better C++ programmer as well, learning the Rust patterns.
Yeah, definitely. Yeah, because so Rust, like I often explain that, like the Rust is not able to compile every single like kind of like safe programs, but at the same time, the subset that is actually it is able to compile is very canonical at the end of the day, right? So if you structure the same way your C++ that you would do with something that compiled with Rust, you do have like a way more manageable, references and so on in or less like undefined behavior in C++, I guess.
All right, just one more question before I open up the floor. What topic would you like to see here at Tokyo Rust talked about?
You know what? The next one you mentioned there, because we use mmap in Copper, because we like on bare metal you can imagine we hit like the file system, the block device like straight, but on Linux we use mmap, and there is like unsafe everywhere in my code base to actually touch those piece of memory. So if there is a safe way to do mmap, that would be amazing. So you already have it.
Thank you. Unfortunately, Alex is not here, but Alex, if you're watching this, the pressure is on. Thank you. Great.
We need to talk.
All right, and now we're going to do Q&A. This is how.
When you were talking about how it's scheduled and that it always runs in the same loop, I was kind of wondering if this is inspired from languages like Esterel or Signal or Lustre, like the synchronous programming languages.
No, so the funny thing, so I have to tell you, right? I'm not academic at all. Like I'm a pure engineer. I'm trying to do shit to fix stuff. Right? That's it. Right? And that's so funny because like after that, like when I built Copper and so on, I realized like never looked at what's the underpinning, like the theoretical underpinning. And there is something that's called lingua franca. You can check it out. And when I read the paper, that's the fastest research paper I ever read in my life, because that was exactly Copper. like not more, not less, exactly Copper. And so I read through it as, yeah, people thought about that like, I don't know, a few years ago already. But they started a company, but the thing was not that good, unfortunately. But people thought about this, those type of like kind of like chain of events that needs to be repeatable, deterministic, and in a highly kind of asynchronous environment in terms of like execution, multi-threading, and so on. So yeah, no, it's not the first time that people thought about it, and I'm not sure why nobody actually built it. I did the opposite.
Thank you for coming. Really appreciate it. Hope you're enjoying Tokyo.
It's amazing, always amazing.
Okay, well, I had two questions then. I'll ask the technical one first, and then I'll ask you the Tokyo one. I hope this is listening. First of all, thank you for saying what you said about learning Rust. Make it work, make it good, make it right, make it fast is always the right way to write software. I think it's more than ever now with agents who can like just spit out everything. So, but one thing about Copper that stood out to me before when looking through it, and also in your talk, is you have to know what all your missions are kind of beforehand. And so what happens if you have some kind of dynamism? So like one company I know of here in Tokyo, one of the things they're trying to do is have modularity. How do you have to know ahead of time when you deploy your robot all the possible modules and pre-make all those missions, or is there a way to have kind of dynamic loading of your modules, like so that you can have your schedule in Copper?
No, that's a very good question, and that's really like a kind of like that's the opinionated side of Copper, right? You already pinpointing it, right? So with Copper, you have like a notion of missions, means like kind of like think about modes, right? Like you would have, let's say, a robot that you deploy for data collection, for example. Maybe the behavior and so on might be different that when they are actually truly autonomous. Right? So we have that notion of like that flexibility of like saying switching like a multiple switches to actually make your robot have a behavior or another. But it's kind of like restricted. The thing is like a pure dynamism. In practice, it almost never happens. Like, okay, you fly a drone, it's over your head, and you say, oh, like with Ross, like let's subscribe to a new topic with like a new task that is starting on your drone. Never happens. Never happens. So that's a little bit like from that observation that I built. You know what? The more static stuff you know ahead of time, the more you can optimize, the more you can repeat. And that's how I went from the other side. So basically, mainly static, and I did like some flexibility with missions and configurations. You can change configurations and restart. That's also possible. But nothing that pops up in your drone when they fly, or your self-driving truck at 120 kilometers per hour on the highway. It won't happen.
Okay. Fair enough. And then the second one is a kind of a personal question, but since you alluded that it's not your first time in Tokyo, what would you say is outside of talking at Tokyo Rust? What is like your highlight? One thing that you loved that you did that is not on TripAdvisor.com?
Oh wow! Guys, that's going to sounds very stupid, but I think that's okay. Started pickleball recently, and so it's not really popular here in Japan, right? Like nobody know this game. It's very popular now in the US, and there is like a pickleball court at the bottom of the Tokyo Tower. Like what? So I played pickleball, this thing that is unknown here at the most known place in Tokyo. It blew my mind. I was like, what the hell is going on here? So it was fun.
How you synchronize different lengths of frequencies with your frequency of your program?
So sorry?
So how you synchronize your sensor frequencies with your frequency in your program to fusion the data?
Oh yeah, that's a good question. So our loop can be very fast, right? We have like sometimes robots can go like 2 kilohertz. Like you can limit that, like if you don't need it. Like sometimes robots are slow, right? But then it gives you a kind of like a sampling in time about like the data that is coming in, and we have what we call like an aligner that is very powerful to do that type of things, like saying how do you match. Basically, you have like I don't know 5 sensors, and how do you match them in time, right? So you can reason on the same state of the world, even if there is some buffering, or like I don't know, you have something on USB, it's a bit slower, or something on a PCI bus that is coming quicker, or like different rates, and you can buffer them and align them, and then present that to your algorithms. Usually, people do that with in robotics called sensor fusion. So we have a module dedicated for this to actually reconcile those things, and all those timings. If you look at copper, they are called time of validity, which is very robotics kind of notion, where basically when you get a piece of data, you need to know from when in the world, like literally when photons hit a camera, or like when a LiDAR actually bounce back, you need to know that timestamp, right? And that's what we are basing that synchronicity on, like on the actual time of your sensor.
Great, thank you.
Thank you for the good talk. So can you quickly go over what makes ROS not an actual operating system, and what makes Copper an actual operating system? Because I missed that.
Okay. So if you talk to, I mean, the kind of the operating system, like denomination, or I don't know, like a kind of name, has been kind of overloaded, right? An operating system for me, like is something that is running bare metal on your like a Linux kernel, right? That has like has drivers and actually file systems and scheduler and so on and so on, right? That's for me what an operating system is. ROS doesn't do that at all. ROS is just like a middleware and components on top of that middleware, which is like a layer on top. It needs Linux. With Copper, we can run on Linux because we can run in a process, but we can also run bare metal, like literally with no operating system at all. We do have a scheduler, we do have a file system management for like errors and so on, right? So,
is there something like a kernel also?
Yeah, it does. Like when you compile Copper, like literally this is a huge proc macro in Rust that compiles a kernel just for your robot.
Okay.
That's how the thing is actually like that fast. Imagine like a Linux that is actually compiled just for your application and knows exactly what's going to happen in your application, which is not true for like even an RTOS doesn't know what's going to happen. Copper knows, right, ahead of time, which is the kind of a plus. That's why we hit at that level.
So thank you for the talk. So this is branded as a Rust and AI thing, so I'll hit you with like an AI question.
Yep.
Have you, or maybe like a client or a customer, experimented with using Copper in combination with something like Burn to run inference kind of entirely on device and make decisions according to that as well? Is that something that is like a supported use case, or is maybe the latency kind of too high for that type of application?
Yeah, so no, good question. So yeah, of course, like today, I mean now we don't have like a lot of robots like just running on like let's say what we call I don't know. Regular, or like a kind of historical, like robotics algorithms. You will find ML, right? So we do use Candle. You know Candle. They are built by Hugging Face, and you have access to like a huge library of like pre-made kind of algorithms and models and so on. And you can extend it with your own too. So some people use that. Some people use like more runtimes that are based on Onyx, which is like a kind of standard way of like describing those models. So yeah, I've seen those too. And some people also wants to be able to experiment a bit more. So we do have like a task that can actually run Python, right? Like through Py03. And one of my customers at some point, like I was like, okay, I'll give you that. I'll give you. They were like, oh, we need to be able to run Python because, like usually ML engineers, they are not Rust at all, not even C++. Usually that's Python. But that's also another way, for slow robots, it's fine. But if you run like those long inference, and we have a way to keep it deterministic while in background, because you can imagine if you have an inference that takes like, I don't know, 500 milliseconds to actually be there, you don't want to lock out your robot. So we have a way to basically park that on a thread pool. Okay, there's going to be a long task, so it's not like hardcore, real time critical. And then at some point it will actually publish their results. So that's for your second part of your question. So yeah, we do use that. I'm super excited about like what NVIDIA released recently. The fact that you can compile Rust on GPU, finally. I haven't tried it yet, but that's super exciting for Copper too, because that would like give people like a kind of a unified way of programming their robots and tool chains too.
Yeah, thanks for the talk. My question is also related to AI. Like, do you have projects already working with Jan LeCun or something about the modern way of how robots should work? Like, not setting them up like based on LLMs because it's way too slow, right? Like this system of like Kahneman system 1 and 2, like thinking slow and fast. You know, like I wonder if, I mean, in our brain the most neurons are in the cerebellum, like making us doing stuff without thinking, right? And this kind of world model stuff and what Jan LeCun is doing, I think is super cool. And yeah, is there a project already you have maybe where you
not
work
yet,
with them? But
not yet the closest.
Because the latency could be really cool, right? If you bring that together with the new AI models, which are really fast. And
No, definitely. I'm excited by that field and looking it up also, right? And being able to, so you have a precursor to this, especially when you are doing like end-to-end models, like you are doing a robot that is basically a huge black box. Usually you want to have something aside, so we experimented even in the past, with like reflex systems. It's almost the same thing, right? Like where okay, you realize that an event happened on your data stream in your sensors, and you understand that I don't have time to actually go through the entire like scene understanding of what's going on. We need to react right now, right? So some customers are doing that, like the kind of like two-tiered, but it's not like two-tiered ML. It's like ML and then like something that's going to be really brutal, like think about an ADAS system for a car. Like it's gonna do like something absolutely like degraded compared to the normal behavior. But definitely there will be like for sure progress, because like today high-level reasoning is like so slow that, and so also like power, like you'll use a lot of power just to go through one cycle of those, right? So no, definitely excited about those research advances.
I have a quick question. I believe Rerun has an impressive real-time series database. Do you integrate with Rerun?
Yeah, we do. Rerun works so well with Copper, and actually we do. Actually, another question that might come up is how do we make money at Copper? We sell actually tooling, and we do have like a specific debugger for roboticists that is based on time and not line of code. And we do use Rerun, for example, for the visualization side of this thing, right? So, and to visualize like it's not Rerun this one, but like often like when you want to visualize with Copper, you just make like a quick task that subscribe to one of these data stream, and we are already compatible with like the way Rerun presents stuff. So yeah, it's so easy, like 2 lines of code, and you have something that you can visualize.
Thank you for your talk. So you mentioned that roboticists are very resistant to change. I'm curious if there has been a feature in particular that makes roboticists go from this is cool to we need to use this now, because I have a lot of coworkers, they're always complaining about ROS, and so I'm kind of curious, like what would be like the one task you would recommend someone use Copper for, so that they're like kind of sold on the idea?
Yeah, from my experience with my customers, right, or those users, determinism is the one. Like literally, they suffer too much. Imagine like debugging a ROS robot today. You put like a breakpoint somewhere on one of your tasks, and the rest of your robot continue to run. So you have no idea about your state. You cannot really restore your state. it's really hard to reason about. You show them Copper with like the debugger where you can jump in time, restore the entire stack, like observe every single field and do like step by step exactly what's going on and change their code and replay that deterministically and see the difference between the two. They are like, okay, this is it. Like that is actually cutting like the cycle of development of robots by so much. That usually the one that puts them over the ledge. The second one is safety, because like a lot of people are like, cool, what are we doing, right? Like literally they are building end-to-end models that are running humanoids, and those things can go through drywall, and they are like, okay, you want to sell that? Like they all tell you, oh, you know what, it's okay, it's available, 20K, and you have your robot and so on. You want your kids around the thing? I'm not sure, right? Like, so that's also the second thing that they will, at some point, for all those robots to be useful, they will need to be near people and powerful enough to be useful. And that means that you will need to have something that is kind of repeatable and safe for those use cases.
All right, let's do 3 more questions.
Hello.
Hey.
Very nice presentation.
Thank you.
So I've got a question, and I mostly see some answers on the board. So the question is about like application of your framework. So as far as I see, it's more like low-level control. Is it like for low-level control systems or programs, or how do you like see the application, or maybe you envision like the scale of application using Copper?
Yeah.
So I also saw like you have Xeno, so it means maybe it talks over network.
Yeah.
You can like run maybe multiple graphs of this Copper, or like what's the application you have seen, or what's your vision?
Yeah, so that's why I put that there, like several applications there, and it's not like, I mean, that is actually a vision system and sensors and so on. There are like motion planning. That's if you look at it, that's the University of Utah building like a little AMR that is autonomous, like that understand the ground and actually move. It's for a lunar application. We have this one also autonomous, like for the last mile delivery. This one for inspecting solar panels. So we have a lot of like fully autonomous, like from end-to-end applications. We have also a company doing drones also, like a little bit less, like more like in a control side and more like a flight control type of things, but still, right? Like you have like a bunch of applications that are mainly in like autonomous robots, right? Like so what you usually don't see here is like robots in very like control environments where time, you don't really care about the real time, right? Like for example, like an arm in like, I don't know, like a conveyor belt that takes parts and I don't know, do stuff with that. Hey, use ROS, it's perfect. Like you can stop the world for 30 seconds and you're fine, right? And if you drop the piece, nobody's gonna get hurt, right? So you see the class of applications also, right? Like so, autonomous robots in like a dynamic environments. That's gonna be the main application here.
I just wondered, it looked more like a low-level controller application, or it's like you can build a full robotic system with Copper.
No. This one is completely full with like ML for computer vision, motion planning, actuation, like a high level like body control for their thing, and the low level control applications like. So yeah. You see a lot of like control stuff with Copper because of course I started from bottom up, right? So that's why like a lot of things that are already available, like I don't know, IMUs and so on, like are about like controls, but I don't know. We have like a 3D camera with like the Z cameras that are supported, bunch of lidars and CV algorithms also. It's very complete now.
So it's like one huge graph, like one huge Copper graph for a single robot, right?
For a robot, yeah, usually, yeah. For example, in self-driving, we, for example, at Arago, we had like more than 200 tasks on our robot. So even like when you have like end-to-end systems, your end-to-end system is going to be only part of your robot. Like let's say, imagine like a self-driving car. When do you allow to open a door, or when do you, I don't know, put it in safety mode, or put the flashers on, or and so on, and have like layer of safety on top of it. So usually you do need pretty complex graphs like around your main algorithms in robotics.
Yeah, so I guess like if there is a panic, it will be a big problem, right?
Yeah, usually you try to avoid panics, right? We do install like actually a panic handler on Copper for that. Like we need a behavior from the developer saying like if this thing panics, what do you do, right? But yeah, there are people usually use like several like processes also. You can distribute Copper, of course, and that can actually help. There is another question there.
Yeah, okay. Just a quick question about sensors. So
yep.
you have always some kind of drift in sensoring. So how do you cope with that in your Copper system? Is there kind of sim to real? Is this a keyword?
So we don't. I mean, that's a little bit out of scope for Copper, but like some of our customers do like a dynamic calibration. So you can you have like algorithms like observing the world from your sensors and realize that like especially if you have like several like sensor modalities, realize that they start to get misaligned, and you can actually keep on running. Usually the step 0 of that is like you detect that something is kind of wrong and you stop, and then they evolve like and self-calibrate. Like Tesla, for example, is doing that with their camera with like lines on the road, and they actually realign their sensor. And you can do that same thing in terms of range. Like if one camera detects like like a range of luminance that is different from another one, you're like okay, there is something off, and they recalibrate those cameras in real time. So yeah, it's a little bit out of scope. Like that's going to be like a task that you would implement on top of Copper.
So a lot of software that you see on the web, is infected with ideas about the kinds of people who work on the web. And the thing that comes up is you look at old books, and they talk about different formalisms and frameworks for like testing their software, and particular like making state machines explicit and checking the specification, all that, which it feels like would actually be worthwhile in something like robotics, right? Or something where like you said, where people are in danger if it's not done correctly. Yep. And I'm curious to hear what stuff nowadays like is used, and then how Copper makes this easier.
Yeah. So okay. Like so the question, like if I try to reformulate that, is like traditionally you need to have a kind of a verifiable system. Okay, you can know all the states of what you're doing, especially in the safety world. And for sure, like in like applications, like let's say you would make like let's say an ML algorithms on one side of the system and kind of a checker on the right hand side. You would need to actually verify this, right? And so there are like Copper is not like special in that sense, where you do have like input outputs. The thing is like it makes like the modules pretty clear, right? So you have the boundaries of what are the inputs and outputs, so you can take your component, and then you can kind of verify those components independently and at the level of like safety you want, right? Like usually like safety norms, right, or like safety certifications go like through, okay, you kind of tested like most of the cases, or if you want to be really safe, you basically do like exhaustively like all the inputs, all the outputs, and like that on that sense, like Copper, because it's like hardly like there are like strong types in Rust. Like if you have an enum for a state, for example, it's going to be okay. You have those states, you can test them all. Same thing for any things we have like as a standard message. You have a very strong type input. That helps for that thing, right? Like in terms of like state machines, we don't have a standard way of actually making state machines. Like a lot of people are actually building them for Copper. It's very common in robotics, actually. You do have like those behavior trees where you navigate the things where you change your behavior. But people have implemented behavior trees for Copper, but I don't have like a kind of a standard components that might come at some point, because like again, that's linked to all that story about like how you test and how you go to at the boundaries of your system to be sure that it is still in a safe state.
All right, thank you for answering all these questions. I think that was by far the longest Q&A we've ever had.
Yeah, and my talk was long.
That's a great talk.
Thank you
for
so much,
joining
everyone.
us. Let's give Guillaume a hand.